A colleague asked me the following question. Suppose a ship is illuminated by a vertically polarized seeker. How can the ship's skin echo, which is the reflection of the vertically polarized radar signal, have both vertical and horizontal polarization? So this is my answer. I don't warrant it to be comprehensive, but it's how I think about what's happening. So to start, for simplicity, imagine a flat, square metal plate oriented at, say, 45 degrees, and a vertically polarized electromagnetic wave impinges on it. The electric field can be decomposed, the vertical field can be decomposed into a component that is parallel to an edge and a component that is perpendicular to that edge. The field component, which is parallel to the edge, will cause edge currents, and these currents will cause re-radiation. Radiation by the edges can be represented mathematically as a bunch of infinitesimal dipoles lying along the edge. They're called Huygens sources, and we know what their polarization looks like. It's the same as a dipole, a bunch of arrows that point from one pole to the other. And the result is that the field radiated by the edge currents will include a horizontal component. Now, in order to calculate exactly what that horizontal component is, you need to use mathematical methods called physical optics. Now, the central part of the plate will re-radiate vertical polarization. It's easy to visualize that the impinging field causes sheets of electrons to vibrate up and down in the plate, and when they get to an edge, they follow it since there's nowhere else to go. The total reflected field is the linear sum of the field from the center of the plate, loosely speaking, and from the edges. Now, as a separate mechanism, polarization twisting can happen when two reflections combine coherently such that the path difference is, for example, 180 degrees. This is how a twist mirror works in an inverse Cassegrain antenna. A twist mirror converts polarization from one plane to the other plane. It has wires at 45 degrees in front of a metal backplane, and the distance between the wires and the backplane is a quarter wavelength measured in the dielectric material between the wires and the backplane. Now imagine a vertically polarized field impinges on the mirror. The component that's parallel to the wires is immediately reflected. There's a sign reversal which we'll ignore for simplicity since it doesn't change the outcome. If the wires are closer together than a quarter wavelength, then the grid of wires behaves to the parallel E-field component like a solid metal surface, for that polarization component. On the other hand, the component of the E-field that's orthogonal to the wires goes straight through past the grid, so it's not there. Now the field perpendicular to the wires has traveled half a wavelength farther than the component that was parallel to the wires, quarter wavelength in, quarter wavelength out. When we do the vector addition, vertical polarization has been converted into horizontal polarization. Now notice that this effect is frequency dependent because it depends on the separation between the backplane and the wires. So if the frequency changes and the wavelength changes and the parallel and perpendicular components don't differ by half a wavelength anymore, it's something else. Expect the reflected signal to include primarily the incident polarization, but also other components including the orthogonal polarization and elliptical polarizations.